This is my third time, and this is the most challenging lecture for me, for us actually. This is the end of the day, and you are nicely exhausted by skiing and the snowboarding, and it is my responsibility to keep you awake and to amuse you. Okay, so this is the Saas lecture, and the galaxy formation 2 continuation. At the end of the last lecture, I talked about the stellar population thing of the Lyman-alpha emitters. And then in this lecture, I will cover the luminosity function, morphology, and interstellar medium state. So this is the advanced notice. So I will ask you a question. What is the most important physical characteristics of Lyman-alpha emitters that are distinguished from the other high-Z galaxy populations like the LBGs, FZDK, SMGs, and so on, and why? So I will talk a lot about the properties of the Lyman-alpha emitters. Some can be compared with the other population. All right? So this is important. So then I move on to the other Lyman-alpha luminosity function thing. So Matt Hayes nicely talked about the reddish zero Lyman-alpha emitters, as you learned. So well, this is the great last sample showing the great morphological information. And well, at redshift 0, another effort of the low-Z Lyman-alpha emitter studies are made with galaxy grism. So great thing of the galaxy grism is you can obtain the flux limited sample, so you can derive luminosity functions down to the detection limit of the galaxy grism data. So well, the first result was announced by the De Haven et al. 2008, and they got the very low number density of the Lyman-alpha emitters at redshift near to 0. So the number density is about a few times 10 to the minus 4th, which is about the 20 times smaller than the Sloan Digital Sky Survey galaxies. So let's look at the luminosity functions that they derived at redshift near 0. So this yellow thing is the galaxy result, luminosity function, the number density as a function of the Lyman-alpha luminosity. And it compares the result of the redshift 0.9, 2, and 3 to up to redshift 0.5. So as you can see, there are two important features in the evolution of the Lyman-alpha luminosity function. One is the significant increase of the Lyman-alpha luminosity function from redshift 0 to up to 3. And the other feature is the from redshift 3 to 5.7, you find small difference or nearly constant. So these are the best fit Schechter parameter error contours, and phi star for here, and the L star is here. For the redshift 0.3 is shown with the yellow line, and 0.9, 2.2 to up to 5.7. So the very interesting thing is from redshift 0.3 to redshift 3, there's a very strong evolution. Well, from these contours, probably the Lyman-alpha luminosity, L star gets quite bright. And of course, again, you will see the constant luminosity function from redshift 3 to 5.7 in the Schechter parameter space again. So let's look at these features more closely. These two, increasing luminosity function from to up to 3 and constant luminosity function at redshift 3 to 6. Okay. So first, redshift 0 to 3. So to characterize this evolution, you can derive the Lyman-alpha luminosity density, integrating the Lyman-alpha luminosity function with the luminosity like this. Then you have the Lyman-alpha luminosity density from redshift 0 to 6. And interestingly, from redshift 0 to 3, the evolution of the Lyman-alpha luminosity density is about a factor of 30. It's very, very big. If you compare it with the UV luminosity density evolution, it's a factor of 7. And also, if you correct the dust extinction thing, like Madal-Lilly plot, star formation rate density increases up to a factor of 10 from redshift to 0 to 1. So this strong increase of the Lyman-alpha luminosity density tells you that Lyman-alpha is something special, not the following the simple star formation rates. So then let's move on to the next evolutionary feature from redshift 3 to 5.7. So that is the pretty constant. But well, it is surprising because if you know UV luminosity function evolution given by the Lyman break galaxies or dropout galaxies, from redshift 4 to 6, it shows significant decrease. So it is great contrast between the Lyman-alpha population and the dropout galaxy population. Of course, you are looking at the UV luminosity for dropouts and Lyman-alpha luminosity for the Lyman-alpha emitters. So let's look at it more closely. So this shows the Lyman-alpha emitting galaxy fraction given by the Keck spectroscopy targeting the UV continuum selected dropout galaxies. So you have the dropout galaxy sample from the broadband selection, and then you carry out the spectroscopy, and having the same luminosity limit and the same equivalent width limit. So how much fraction of the dropout galaxies have the Lyman-alpha emission line? So this is the idea, and then well, it has the dependence of the equivalent width, but basically the Lyman-alpha emitting galaxy fraction is increasing from redshift 4 to 6. So in other words, so this indicates that from at redshift 6 for L-star dropouts, about a half of the dropout galaxies have Lyman-alpha emission line. So it's surprising. So like something like this. So at redshift 3, you have about 1/10 of the dropout galaxies are showing Lyman-alpha, but at redshift 6, so about a half of the Lyman break galaxies are showing the Lyman dropout galaxies are showing Lyman-alpha emission line. So it is a significant evolution. And of course, this evolution is also quantified using the Lyman-alpha escape fraction. So I will talk about the two escape fractions. One is this Lyman-alpha escape fraction. The other is ionizing photon escape fraction. So this time, Lyman-alpha escape fraction. So this Lyman-alpha escape fraction is defined by the luminosity or luminosity density of the Lyman-alpha divided by the expected Lyman-alpha luminosity or luminosity density, which is estimated with H-alpha flux or UV luminosity and so on. So assuming the case B recombination. So here 8.7 is the you're familiar, case B recombination rate, the factor. So Matt Hayes nicely shows this evolutionary track from redshift 0 to 6, and showing the 2 orders of magnitude increase of the escape fraction. So this is another format of the increasing Lyman-alpha population towards redshift 6. So, but why you have more Lyman-alpha emitting population at redshift 6 than 3? So, well, probably, I think it is easier for us to think about it on the basis of UV continuum magnitude, or MUV. So, left panel shows the Lyman-alpha emitting fraction as a function of the magnitude. I previously showed this as a function of the redshift, but this is as a function of the UV magnitude. So, everything is used in this range. So there is a trend of the increasing trend for the fainter population having the more chance of the Lyman-alpha emission. So in other words, majority, about a half of the faint minus 19 magnitude, sources have the Lyman-alpha emission of the 50% of Lyman-alpha emission. So this is the same. This is the analog. This relation is the analog of the Andor relation, which was suggested in the 2006 by the Andor et al. And also another important piece of evidence is the UV luminosity function evolution given by, say, Buens and many others. So this is UV magnitude as a function of the number density. And yes, the number density from redshift 4 to 6 decreases. However, towards high Z, faint end slope alpha is steepening, right? So in other words, not much decrease of the faint, intrinsically faint, continuous faint population. So if you combine two of them, so towards high Z, you have less, bright population. In other words, less, no Lyman-alpha emitters. But for high Z, you still have the many continuous faint sources which are emitting the great chance of the Lyman-alpha emission line. So in this way, you can understand the why you have more Lyman-alpha emitters. So in other words, intrinsically, just for high Z, intrinsically faint, continuous faint, and the Lyman-alpha emitting population remain. Or that's the early epoch, so it appears early first. Then the bright population with no Lyman-alpha emitting population appears at redshift 3 or so. And also this idea is pretty, explains the nearly constant abundance of Lyman-alpha emitters because the UV continuous faint population is still large. But you have the high Lyman-alpha emitting fraction. So the number density of Lyman-alpha emitters may not be changed. So, and also this is another format of the increasing importance of the Lyman-alpha emitters from redshift 3 to 6. This is a result of the HEDDEX pilot survey, and from redshift 3, the total, the Lyman-alpha emitter contribution to cosmic star formation rate density was about the 1/10. But at redshift around 6, it's about unity or about 50%. So probably the Lyman-alpha emitters are major galaxy population at around redshift 6, and probably this trend would continue because you go higher redshift and less dust, less metallicity, and more chance of the Lyman-alpha emission line. So you expect more Lyman-alpha emitters beyond redshift 6. But beyond redshift 6, in the IgM is pretty neutral, so you may not identify, you cannot observe strong Lyman-alpha emission line because of the absorption of the neutral hydrogen in IgM. And I move to the other different topic. So second topic is the morphology. There are many other attempts to measure the morphology. And even from the 1996, Pasquarelli et al. Nicely measured the size of the Lyman-alpha emitters using the HST UFPIC2 data. And actually, their claim is pretty the same as we saw in the HST, ACS, and Ouchi data. So right panel shows the Stephen Fickel-Stiles result of the HST imaging for the redshift 4.5 Lyman-alpha emitters using the narrowband filter to look at the morphology of the Lyman-alpha emission, and also the I-band filter for the continuum. So in both cases, the sources are pretty compact, like the 0.1 arcsec, or some are less than 0.1 arcsec, so unresolved. And as you can see, there are some the offsets between the narrowband or Lyman-alpha and continuum. And similar, the multiple sources can be found in the single Lyman-alpha emitters. But well, these components in continuum components are still very compact. To quantify the sizes of such a continuum sources, and you can compare this with the effective radius of the Lyman break galaxies. So this is the effective radius of the Lyman-alpha emitters, and comparing the those of the Lyman break galaxies. Although the Lyman-alpha emitter shows pretty the large diversity of the size showing with the error bars, but on average, Lyman-alpha emitter continuum sources have the effective radius of say around 0.6 kiloparsec on average from redshift 2 to 6. And this is this is constant, but if you look at the Lyman break galaxies, as you know, effective radius is decreasing towards high Z by 1 plus Z. So it is very good contrast. LAs do not show the significant evolution, but Lyman break galaxies shows the significant evolution, and at around redshift 6, they are touching. So in other words, as I said, maybe these LBGs and LAs, well, selections are different, but maybe you are looking at the very similar galaxies at redshift 6, because many of the Lyman break galaxies are showing Lyman-alpha emission line. So then I move on to the third topic, and so are you okay? So a lot of things inside. So, and I think this is the most exciting thing. Well, so then let's look at the interstellar medium of Lyman-alpha emitters. I got many questions from you about the dust or the metallicity from you during the coffee break. But well, this is very interesting because the Lyman-alpha emitters are characterized by the ISM. Well, so the bit, I first, let you know, want to show the, general feature of the interstellar medium. Well, it is, of course, it's a kind of common sense for observational astronomers. But, well, there are three regions of interstellar medium. One is the H2 region, or ionized region, filled with the H plus ionized hydrogen. And the second one is the photodissociation region, or PDR, which is filled with the atomic hydrogen. And the third one is the molecular region, filled with the molecular hydrogen, or H2. So in local galaxies, most of the interstellar medium is locked in the photodissociation, PDRs, okay, photodissociation regions, where the UV radiation is leaking and to photodissociate the molecules. And these are this shows the temperatures of the H2 region, PDR, and molecular region for the 10,000 K and 100 to 1,000 K and the 10 to 100 K. So, well, as if this is true, then the photodissociation region is quite representative of the ISM, but well, it is very difficult to characterize the ISM state, like the metallicity and the ionization state and so on. So what people do is to just focus on H2 regions for measuring the metallicity and ionization parameter and so on, because they emit strong emission lines, which are useful to diagnose the metallicity and so on. And interesting thing is the metallicity, and to estimate the metallicity of the galaxies, there are two major methods. One is the direct temperature method, which uses the oxygen 3, 43, 63, and nitrogen 2, 57, 55, and so on. So which are called the auroral lines, and This is the example of the other O3 4363. This is very, very weak. Right next to it, there's a H gamma line. So as you know, H gamma is so weak, but still weaker than the H gamma for the other O3 4363. And the strength, the flux is about 1/70th of the 5007 for the other 4363 line. So you need the other lensing effect or stacking analysis to get this line. And another method is to use the other strong emission line, like the popular one, O2 3727, and O3 the 507, H alpha, H beta, and nitrogen 2. So, well, actually, the direct temperature method is, of course, as you know, the very good indicator of the metallicity. This is because so this shows the galactic H2 regions, metallicity as a function of the electron temperature in unit of 10,000 K. And as you can see, there's a very tight correlation between the metallicity and the electron temperature. This is because if you have more metals, then the metals work as the coolants of the ISM. So it has the less lower electron temperature. Okay. And then the next thing is that how you can measure the electron temperature. Well, maybe as you know, if you go back to the Osterblock's textbook, it tells you the answer. Well, using the 4363. So this is this shows the transitions of the oxygen 3, and well, as you know, 507 and 4959 are the prohibited lines. So the 1D state here, so electrons stay long. So if the temperatures of electrons are very high, then you will get more chance of the collisional excitation to here, and then you get the 4363 line. So in this way, if you have the higher temperature, you have more 4363 lines, and this shows the ratio of the oxygen 3507 divided by the 4363 as a function of the electron temperature, and there's a strong relation. And so if you have these lines and line ratios, then you can measure the electron temperature, and then you can bring this and estimate the oxygen abundance based on the simple physics, like using the temperature terms and the line ratios. So in summary, O3 4363 and 507 are used to obtain estimates the electron temperature. Then you can easily get the oxygen abundance robustly and with the simple photoionization model. So it is great once you get the 4363 line. That is very difficult to observe though. And the second thing is this is extremely popular thing is to use the strong emission line. One is the R23 index, as you know. So R23 index is the ratio of the sum of the O2 3727 and O3 507 divided by the H beta. And this right panel shows the R23 index as a function of the oxygen abundance. And this dashed line shows the empirical relation calibrated by having the O23 index and also the direct temperature method calculation. So you have this, and you have many solid lines here. So these solid lines are photoionization models changing the ionization parameter. So ionization parameter is defined by this Q ion, so which is the ratio of the ionizing photon emission rate divided by the area of the sphere of the Strömgren sphere, and times the hydrogen atom density. So in other words, so excessive. So in short, ionization parameter is excessive, ionizing photon per, given a hydrogen atoms. So how much, more excessive, ionizing photons exist. So as you can see, that calculated relation shows very different from the single ionization parameter sequence, but it's changing, okay? So it is interesting. And also this R23 index once you get the R23, and then you have two solutions, high metallicity solution and low metallicity solution. This is because for high metallicity branch, far infrared fine structure line cooling works. So more metallicity has the less R23. Another thing is for low metallicity branch, you have more collisionally excited O2 and O3. So such a R23 fluxes get weak. So in this sense, you have the two solutions. So it is not good. But there is another famous index which is named the N2 index, which is the ratio of the N2 for 6584 divided by the H alpha. So as you can see, there's a very simple non-degenerate relation. So but there's a problem that the nitrogen 2 is extremely weak for the metal poor population, less than 1% level. So you cannot measure accurately. But if you compare, use this N2 index and to resolve this degeneracy of R23 index, then you can easily get the metallicity combining these two relations. So there are no direct temperature method measurements for the metallicity of Lyman-alpha emitters, but using the strong lines of the H alpha, N2, and O3 5007, and so on, the other people have estimated the metallicity of the Lyman-alpha emitters, and of course, the numbers are limited, but the typical Lyman-alpha emitters are estimated to have the 0.3 solar metallicity. And on the other, if you plot the Lyman-alpha emitters on the mass metallicity relation, then this goes below the local relation, or it is consistent with the Lyman break galaxy result. And if you look at the fundamental relation, or more, how do you say, neutrally, I say, mass metallicity star formation relation. So this is the result of the mass metallicity star formation rate relation, and the results indicate that this is the Lyman-alpha emitter stack, but it is pretty consistent with the star formation mass metallicity relation. So, and so far, we have not seen any extremely metal poor Lyman-alpha emitters. So one of the reasons is that we can detect such strong lines for the very bright population of the Lyman-alpha emitters. So that's why we think the metallicity is pretty comparable to the one of Lyman break galaxies. So maybe we need the lensing technique or stacking technique to get more average metallicity of the Lyman-alpha emitters. Okay, and exciting thing of the interstellar medium of Lyman-alpha emitters, I think this one. So this is the recent result, and of the spectroscopic observations for the Lyman-alpha emitter, and from the O2 3727 to the H alpha. And what is interesting is that the oxygen 2 is extremely weak compared with the oxygen 3 5007. So if you define O32, which is the ratio of the 5007 to the 3727, the flux ratio is about 10. So if you look at the other Sloan Digital Sky Survey galaxies, they show O32 is unity or below unity. So, well, you may think that, well, this system has the other AGN, but if you look at the other BPT diagram, there's no indication of the other AGN. And you may worry about the other extinction for the other bluest band of the 3727, but this value is got by the other extinction corrected thing using the other Balmer decrement. So why you have this? So this is just a single example, but there are many such a system. So if you look at the O32 as a function of the R23 for Lyman-alpha emitters falling around here, and if you compare this with the Sloan Digital Sky Survey galaxies at redshift 0 and Lyman break galaxies at redshift 2 to 3, so it's still beyond in terms of the O32. So in summary, Lyman-alpha emitters have the O32 about the 2 orders of magnitude higher, and even 1 order of magnitude higher than the LBGs. So it is very large. It shows a very large O32. So this diagram is interesting because R23 is, as I said, metallicity indicator. So this solid line shows the photoionization model changing the metallicity. So if you change the metallicity, well, it moves around here, but it never goes up like this. So then what you need is to change the ionization parameter. So if you, increase the ionization parameter about an order of magnitude this way, so this line can explain the Lyman-alpha emitters. So in other words, if you believe the photoionization model, ionization parameter is of the Lyman-alpha emitters is about an order of magnitude higher than the Sloan Digital Sky Survey galaxies. So then question is that why the Lyman-alpha emitters have such a large ionization parameter? What's the physical origin? Well, if you look at the ionization parameter in a different form, then you get this. So ionization parameter is proportional to the cubic of the ionization parameter is proportional to the ionizing photon production rate and the density of the atoms and the square of the volume filling factor in the Strom-Liouville sphere. So there are 3 possibilities. One is the pretty high ionizing photon production rate in Lyman-alpha emitters. The other is the pretty high electron density in the Lyman-alpha emitters, and the other is the high filling factor. And also the other, well, such a high ionization thing is found in the other strong in other lines, not oxygen lines, but carbon lines as well. So the right panel shows the recent result of the spectroscopy, Keck spectroscopy given by the Dunstack. So this shows the equivalent, redshift 2 lensed galaxies, and this shows the equivalent width of the Lyman-alpha and the equivalent width of the carbon-3 1909. So high ionization line. So well, if the Lyman-alpha gets strong, then you get the stronger high ionization carbon line. So this relation even you can find at the redshift not only 2 but redshift 6. So a strong carbon-3 1909 is detected for the lensed Lyman-alpha emitters. And the same thing happens at redshift 7.05. But well, recent Dunstack paper claims the detection of the carbon-4 15648. So that is a pretty famous indicator of AGN. But well, their claim is that this is not originated from AGN, but a star formation, but a high ionization. But of course, there are no clear signature of the AGN in this system, but still, they should look at the possibility of the AGN. But the bottom line is that in this way, high Z Lyman-alpha emitters are showing very high ionization lines, even for the carbon, not only the oxygen. Then you have the question, so where is the other low ionization lines, such as carbon-2? Well, carbon-2 can be observed with armor. Like, this is a fine structure line, but 158 micron carbon-2 is redshifted to the 1 millimeter band. So there are 3 observation results have been shown, but deep armor observations reached about the 0.02 millijansky in RMS. But these 3, 3 results show that there's no detection of the carbon-2. So, but you may worry that the armor observations may not be sensitive enough to identify carbon-2. But if you look at this diagram, this shows the carbon-2 luminosity as a function of the star formation rate. For the local galaxies, there's a tight correlation between these 2 quantities because the star forming activities make the ionized carbon, or C+. So there is, once you get the stronger star formation rate, then you get the stronger carbon-2. But at redshift 7-ish Lyman-alpha emitters, this is below the sequence, about 30 times below this sequence. So it means there's a very weak carbon-2, which is suggestive of small photodissociation region, which is where the carbon-2 exists. So now we have 2 pieces of the evidence. One is the very high O3 for Lyman-alpha emitters. So meaning the high ionization parameter. So more ionizing photons per hydrogen atoms. So, and also from ALMA observations, we see the weak carbon-2 emission, maybe small photodissociation region. So there are many possibilities, but one possibility is, maybe the density bounded nebula. So something like this. So you are very used to the ionization bounded nebula, which is you have more media than the ionizing photons. So then you can define strong sphere, as you can learn in the elementary astronomy, astrophysics. But if you have more ionizing photons than hydrogen or medium, then you have the density bounded. So you have totally ionized region, and the Strömgren sphere is outside of it. So you only have the high, you have the relatively large volume of the high ionization region than the low ionization region. That you can explain the high O3-2 ratio, and also there's no photodissociation region. So so if it is true, then maybe such a system can still for density bounded system ionizing photons can easily escape to the intergalactic space. So you may easily understand the high escape fraction of the high Z galaxies and also the cosmic reionization. That I will touch in the lecture 6 to 7. So another possibility is the high gas density. As I said, the ionization parameter is proportional to the atom density. So if you have the more dense gas, then you have high Q. And also, if you have the high density, then you have more collisional de-excitation that makes the weak carbon-2, prohibited, forbidden line. So, but in this case, what about the you having the strong oxygen 3 forbidden lines. Still, you have the other strong forbidden lines in the H2 regions, although this is coming from the photodissociation region. So, maybe it may be difficult to explain with this. So, yes, I reached here. Okay, so I talked a lot, and finally, yes, nobody is sleeping. That's good. So let's discuss. So the question again is, what is the most important physical characteristics of Lyman-alpha emitters that are distinguished from the other high-Z galaxy populations, and why? So yeah, please start discussion. Well, please choose somebody else. Well, you have already experienced it twice for the discussions, but please find the somebody else. Getting each other is very important. So please, and start the discussion.